Mr. Yeager. I'm doing another video a little bit more in detail about refraction, especially with Snell's Law and the index of refraction. There is another video that I kind of talk about it. So this is maybe just kind of reiterating quite a few things in that one. But it is something that this year we are pushing a little bit more, that you can calculate out the actual angle of refraction, et cetera, et cetera. We'll also look quickly at what's called dispersion, which is related to refraction and diffraction, the spreading out of light through a prism. So anyway, again, talking about refraction, it's when light rays basically bend as they cross into a new medium, all right? And this is again why we see the straw bent inside a cup of water, okay? The light gets bent when it travels to that new medium, all right? I'm gonna go pretty quickly with some of the stuff because it's already covered in other things, all right? So that's basically that, all right? Again, when it travels from one material to another, all right, it bends, but that depends on what we call the index of refraction. Again, I know it's tough to see over there. That's index of refraction between those two materials, all right? And an index of refraction is denoted as n, and it's going to be just a simple number. It doesn't have any unit with it, okay? It is basically related to the density of the material, as we talked about before. The higher the index of refraction, the more dense the material is. But what it ends up doing is the index of refraction alters, the index of refraction of the material, it alters the speed of light as it travels through that material, all right? It turns out, obviously, light travels fastest through a vacuum, which the speed down here is the speed of light in a vacuum always, 3 times 10 to the 8th. N is going to basically be some amount related to that, okay? Some amount less than that. So the index of refraction is 1 or greater. It's never going to be a fraction. There is no point that the speed of light gets any faster than in a vacuum. The more dense the material is, the less the speed is. And again, it's not going to be a giant change in speed. I mean, when we change to another one, it might be 2.98 times 10 to the 8th. So it's only usually going to be little changes is what the index of refraction is going to be. But again, the larger the index of refraction, the larger the change in the speed of light. So here's just basically a couple examples of the different types, okay? So let's go ahead and do a quick problem. I don't think I have a problem. You will be doing some problems where you have to find the index of refraction or maybe find the speed of light in that material. So you can see vacuum is 1.0. Air is basically 1 as well, 1.0001. When we use air, we're going to round that to 1 because the 0.0001 is going to make almost no difference. So what if I said, okay, what's the speed of light in glass? So the way I would do that is it's n equals the speed of light in a vacuum, which I'll usually abbreviate as c. Okay, so c is the speed of light in a vacuum, 3 times 10 to the 8 meters per second. And that's going to be divided by the velocity in the glass. So how would I solve this? I basically rearrange the equation. I multiply the velocity of the glass out, and I divide in the index of refraction. So this is going to be the speed of light divided by n. So this would be 3 times 10 to the 8, so I say e, divided by 1.5. The speed of light in glass is 2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters per second. So believe it or not, I mean, that doesn't seem like much, but glass is slowing down light by a third. I mean, it's crazy. I mean, it is slowing it down by basically a full third. It's slowing it down by 100,000 meters per second, which that's crazy, okay? But that's the way it works, okay? So that's index of refraction. Obviously, it'll be given to you unless you need to calculate it yourself. And again, it's just a simple division. What that's going to lead us to is what we call the angle of refraction. And so what happens is, again, in the other video I showed this some too, is the light travels on in, hits the new medium, and then will bend, okay? And again, it will bend toward this quote-unquote normal line. We have to always think of this normal line, which is the perpendicular point away from where it's hitting. It'll bend toward the normal line if the index is greater. It'll bend away from it if it's less than what you're entering, okay? Or less than what you're coming from, all right? So since glass is greater than air, it bends toward it, and then when it leaves the glass, it bends away from that normal line. And what we're interested in is that angle between the normal line and that and the light ray itself. Okay. The other one's a little confusing down here, where we have this angle, and again, we only use that angle because that's where it's leaving. Okay. But that is your angle of what's called incidence and angle of refraction. So that leads us to Snell's Law, which is again just a formula you'll get. And this tells you what type of angle it will take as it travels through the material. Either what is the angle that it came in, if you know what the angle is as it's refracting, or what's the angle of refraction. But you need the indices of refraction of both objects. So you can see how this is written. All right, sometimes it's not written this way, but we'll go over that. But we basically have Ni, the index of refraction of where the incident wave is, times the sine angle of incidence equals refraction, the index of refraction, that would be, no, sorry, index, the index of refraction. But the refractive index, which would be for the refractive material, and then the angle of refraction. A lot of times, I like this one, how this is written. A lot of times in textbooks, it's just N1 sine theta 1 equals N2 sine theta 2, where you just have to know this is the incident material and this is the refracting material, if you want to call it that, the refracting material. So that's what we're basically looking for on both of those. Okay, so it's going to probably just identify everything here. Okay, so let's try a problem. Okay, so a ray of light travels through air. It's a smooth surface of water at an angle of 30 degrees to the normal. Okay, what would be the angle of refraction through? All right, and so it gives us all the information there. So let's go ahead and plug this in. This would be, what we do is it would be 1, the angle, the air angle of refraction, times sine of 30, because that's the angle that's going in. You can see right there. We're trying to find this angle under here, the angle of refraction. This will equal the refraction, the water's at index of refraction times sine of theta. What you do here is you divide by 1.33. So that will come out to sine 30, which I think is 0.5. Divide by 1.33, technically times 1, but we don't need to do that. So I get 0.3759, obviously a lot of other numbers, equals sine theta. What do I have to do? I do inverse sine of this number, and that'll give me my angle. Inverse sine, and it comes out to 22 degrees. 22 degrees is the index of refraction, which makes sense, because again, we're going to a more dense material, so it should bend toward the normal, it should decrease. Okay? It should get smaller. So again, that's one way to kind of check your work as you go through it. I already talked about the critical angle and total internal reflection in the other video, so just really quickly one more time. Basically, as you're going from a higher index of refraction to a lower index of refraction, if you keep on increasing the angle of incidence, getting it basically flatter and flatter between the two surfaces, there is a point called the critical angle where basically the light will just reflect right along the surfaces, so it never comes out, so you don't see the object. And if you go above that, we get total internal reflection, where basically it just reflects right back into the surface, follows the law of reflection. So if this is 50 degrees, it'll come back as 50 degrees. Oh, sorry. So this kind of finishes up the last bit that we have. We have a process called dispersion. Basically, this is what happens when light travels through a prism. As you know, prisms can basically diffract and refract the light, basically spread it out and bend it, where it basically separates into the different colors of the spectrum. Okay. Again, each color has a different proportion that it basically bends, where purple bends the most while red bends the least. All right, so that's why a rainbow always looks the same: red, orange, yellow, green, blue, indigo, violet. All right. We're not going to do any math with this. It's just the whole idea. I mean, here you go. Basically, what you see. Again, it's the variation in the refractive index with the colors. Okay. And again, that's basically related to how we get rainbows and stuff. So we don't talk any more about it than that. It just turns out that each type of color light basically bends a little bit differently. Okay, but we're not going to. That's basically all you need to know. Is that it's called dispersion. That is it. All right. Thank you.